In the past few days, we've been spending time looking at galvanic cells. Today, we're going to learn about electrolytic cells. So an electrolytic cell is forcing a current through a cell to produce a chemical change for which the cell potential is negative. So examples of this that some of you may be familiar with are charging a battery. So when your cell phone runs out of battery and you need to charge it, you're forcing current through the battery in a reverse direction, and that is not a spontaneous thing. So metal plating, this is used a lot in jewelry, where you cover one metal with a different metal to put a more desired metal on top. And like I said, this is not spontaneous, it is not thermodynamically favorable, which means that you have a positive delta G value and a negative cell potential. So what happens when you're charging a battery? Well, to begin with, you have to use a current that's greater than the cell potential through the cell to reverse the flow of electrons. When you reverse the flow of electrons, what was the anode in the galvanic cell becomes the cathode, because that is now the site of reduction, and what was the cathode now becomes the anode, because that's now the site of oxidation. And the ion flow from the salt bridge also reverses. And theoretically, this replenishes the battery to its original state, so you should have full voltage. Another use that I mentioned is electroplating, and this is where your calculations come into play. So this is an electroplating setup right here. You'll notice that in the electroplating setup, you only have one container. Your anode and your cathode are in the same container, unlike in the galvanic cell where you have two separate containers. So on a prompt where you are given a picture of an electrochemical system, if there's only one container, then it's going to be an electrolytic cell. If you have two containers, then it's going to be a galvanic cell. So when you're electroplating, you're forcing a current through a solution, which then reduces the metal in the solution. So remember, reduction is the gain of electrons. So if I have a metal ion in solution and I add electrons to that, then I'm going to get that metal in solid form. So that will, and because this reduction happens at the cathode, the solid metal will then plate onto the cathode. So it goes from the ion form to the metal form and deposits on the cathode, because again, that's the site of reduction. So now calculations with electrolysis. An example calculation that you'll have to do is what mass of copper is plated when 10 amps is passed through a solution of copper ion for 30 minutes. So a couple of things that you need to know. Reminder that 96,485 coulombs in 1 mole of electrons. You also need to know what an amp is. And 1 amp is 1 coulomb per 1 second. So that allows you to convert between coulombs and seconds. So let's go ahead and start. We are looking for mass of copper. So go back to boxing what we're looking for. We're given two different numbers here. So how do we know which one to start with? Well, remember that I said that that an amp is really 1 coulomb per 1 second. So really, this 10 amps means that that's 10 coulombs per 1 second. And because we have a ratio here, this is now a conversion factor. And you don't start problems generally with conversion factors, so we're going to start with the 30 minutes as our given because that's not a conversion factor. So we're going to take 30 minutes, and we're going to convert minutes to seconds. So minutes on bottom to let it divide out. And in 1 minute, there are 60 seconds. Minutes now cancels out, and now we're in seconds. And because we have our amps, we can go from seconds to coulombs. And we know that there are 10 coulombs per 1 second. And then we can go from coulombs to moles of electrons because we have the conversion for that. So in 1 mole of electrons, we know that there's 96,485 coulombs. But now how do we go from moles of electrons into moles of copper? So we have to look at the reaction. So we have copper ion, and that's going to go to copper solid. You can tell that from the problem because it's passed through a solution of Cu2+, so that's our copper ion, and mass of copper is plated out, making it a product. So we have a charge of 2+ on the reactant side, we have a charge of 0 on the product side, so to make our charges equal, we have to add 2 electrons to the reactant side. So that means now this half reaction is balanced, so that means that we have 2 moles of electrons for 1 mole of copper. And then we can go from moles of copper to grams of copper. And we know that there's 63.55 grams of copper for 1 mole of copper. Moles of copper cancels out, moles of electrons cancels out, coulombs cancels out, and we are in grams of copper. And then when you punch all of that into your calculator, you should get 5.93 grams of copper. The next type of problem that you could be given is electrolyzing a mixture of ions. So if you have a mixture of ions in your beaker and you're electrolyzing that, and ask which metal will plate out first if a mixture of these ions slowly has current increased. Well, remember that the more positive the voltage, or the reduction potential, the more thermodynamically favorable. And the more thermodynamically favorable, the faster it's going to happen. So that means, so more thermodynamically favorable happens first. Because it's more likely to happen. So that means that our silver will plate out, our silver ion will plate first. Followed by our copper. And then our zinc will plate last. And that is because it's a negative voltage, so this one actually is very unlikely to happen. and would require a great amount of current in order for it to happen. If you have any questions regarding electrolysis, please make sure you bring them to class.